Okay, this is a little problem I made up. I got a triangular force coming down here. It's all coming down through here like this. And what I want to do is I want to find out what the stress is going to be at this point C, just some point in the middle beam. Here's what you're going to do if you're faced with a problem like this on a test. Is first, take a moment at either A or B and try to find out what the reaction is at the other one. So I did here, I took a moment at A to find out what the force would be at B. To take the moment at A, I'm going to take 1/2 times my base, which in this case was 2. That's the distance from here to here, which I did 2, times the height, which is 20. Okay, now do not forget to multiply by the moment arm. I'm going to recommend, what I'd recommend is that you put the units in there, because then if it cancels out, you're going to be sure. So if I put -1/2 times 2 meters times 20 newtons per meter, and I cancel my meters out like this, I will at this point only have 20 newtons. Hopefully it's going to make you think, well, I need to multiply it by a distance because I got to get Newton meters. So this time I multiply it by this distance here. This distance would be 1/3 the total distance. That would be 1/3 times t, times 1/3 times 2 meters. So you could do this to make sure, and then you notice you get Newton meters. Okay, so at this point we're good. And then I subtract, plus FBY times 2. I'm assuming this goes back this way. I'll let this be negative going this way. And let me come back here and do this. And when I do that, I got FBY with 6.67 going up. So once you get that, then second thing is sum the forces in the y direction. I get 6.7 going up minus the 1/2 times the 2 times the 20 plus FAY is equal to 0. Solve. FAY is equal to 13.33 newtons. Alright, now if I want to find say the stresses at C, you can look left or you can look right. The problem being, and to get something like this, it's going to be harder to do left. If you tried to do left, then what you'd have to do, you'd have to break this into a rectangle and a triangle. I wouldn't recommend that. I would say just break it into a triangle, and that's what I did down here. Now this distance here, C, is 1.75 from B. So I drew my piece. Now be careful on a test. This value here, and look up here, is no longer going to be 20 newtons per meter. Not when you get to this point. To find out what the force is here, the distributed load force is, take 20, divide it by this total distance, which is 2, and then multiply it back by 1.75. That will tell your height here. And I did that, and I got 17.5. Now you do exactly what you've done before. You can say I'm going to sum the forces in the y direction. I got 6.67 that I calculated before, minus 1/2 times 17.5 times my 1.75 plus FCY. And again, you don't have to put FCY in there if you want to, but that's going to be my reaction force. And let me just double check that. So I got 0.5 times 17.5 times 1.75. Okay, and then that is correct. Let me shut this off. So what that means is if I looked right here at this point here, I'll blow it up here. I got shear taking place because I have to resist this force that's coming down here, and this force here would be 8.6425 because that's just the sum of this part right here. So this reaction as FCY has to be the same. Okay, so that's my FCY. So that's what I'm shearing across. I got one coming up, one coming down. I have to have that. So, but if you're happy, that you can just go with this. This is your shear force coming across that face. Now at this point, come back here, sum a moment around here because you need to find out how much moment's taking place. I took anything that went this way to be negative. So I said negative 1/2 times 17.5 times 1.75 times 1/3 of 1.75 would give me 0.5833. I did that. Plus my 6.67 times the moment arm from here to here was 1.75. And then actually, it's kind of surprised me. This gave me a positive value. So I got 2.74 coming here. So if I get 2.74 coming up here, actually what's taking place, my reaction, has got to be this way, 2.74. So this one is going back this way, 2.74. Okay, so obviously they have to balance. But look what's happened. That means you're going to get compression at the top and you're going to get tension at the bottom. So now I drew myself a cross section. So I know my maximum tension is going to be here, and I know my maximum compression is going to, excuse me, I'm sorry. Hang on, let me say it again. I know my maximum compression is going to occur here, and I know my maximum tension is going to occur here. So if I'm going to calculate those values, well, I have no P over A, right? I have no forces coming this way that's causing a compression or tensile stress. So all I have to do is worry about the moment. So to find the stress here, I would just come back here and I would say the stress, and I don't know what you call this, we'll call it, I don't know, F. Stress at F would just be my moment, and we got our moment, it would be 2.74. The distance from here, being the center, up to here would be 0.05 divided by my moment inertia, and my moment inertia I already calculated. Hopefully that is right. It sounds like on the test you're going to be given that value. Minus 6, that'll give you the stress at F. And again, that is going to be compression at the top. If this beam is symmetrical, then you can say the stress at G would be exactly the same thing, because my C value just happens to be the same. Now remember, this is your C value, so if you have some funky beam that's not symmetrical, do not say, oh, I got to find the stress here, and let this be C. C has to go from here to here. And divided by the moment inertia. And that gives me the tension there. Alright. Now, if for some strange reason on the test they want to know what the stress would be like at this point, all you're going to do is you're going to take the 0.05 out and put in 0.01. If I want to find out what the stress at E is, which is 0.025, I just take the 0.05 out and put the 0.025 in. Alright, now let's talk about shear. If you need to find shear stress on the test, it's going to be VQ over IT. You go back and you say V is going to be 8.6425. That's the force that's cutting across here, which we got right here, 8.6425. So I put 8.4625. I will divide it by the moment inertia. My thickness is going to be this thickness right here, which would be 0.05. And this is going to be my Q value. Now let's talk about Q. If it says what's the maximum stress, then what you're going to do, if this is symmetrical, you want to find this area right in here, and then multiply it by the distance from here to here. So if that is the case, that would be 0.05 by 0.05. So let's subtract out the Q. We'll do 0.05 times 0.05, and then the moment arm from here to here would be 0.025. Okay, that would be max. That's how you get max shear stress. You do not do the whole thing, because think about it. If you did the whole thing, then this value, you'd have the total area, but you would have no moment arm, and this would go to 0. So you do half of it. It doesn't matter whether you do the left or the right, as long as this is as long as this goes through the centroid, which it will be. All right, now let's talk about this. This is a good point. Please listen carefully. If he asks you what the shear would be at E, for example, what you want to do in that case is go ahead and block this out. Oops, let me get the, I don't want this arrow. Okay, I'm going to erase what I had down here. If I want to find out what the shear is going to be at E, I do not use this area here. I use the area from here out. This is going to be my Q value. It's going to be this times the distance from, do a different color. Let's do a green. The distance from here back to here. So let's see what that would be. Say that's 0.025 from here to here. So that means it's 0.025 up to here. So if I was going to find that, I would take this value back out. And I would calculate that area. I'll do that. I'll do it in black. This height from here to here would be 0.025. Again, it just happens to be 0.025 because this is 0.025. So don't think this is it. It's not this distance here. It's the distance from here to here times the thickness, which is case 0.05. And then I'm going to come up from here to here. I'd have to come up 0.025 plus another 0.125. And being brain dead tonight, let's see what that is. And that would be 0.0375. And that would give me the shear here. If it asks for the shear right here at this point, all I'm going to do, take this back out. Now if that's the case, let's erase this. Let's move this line down. Now my Q value is going to be based upon this area here. So in that case, if this is 0.01, then from here to here it'd be 0.04. So it'd be 0.04 times my thickness of 0.05 times the distance from here to here would be going up 0.01 plus another 0.02, that would be 0.03. And that would give me the shear at this point here. And that's it. I mean, it's not very hard. Just follow these steps. Exactly what I did here, and you should be good to go.